Hi, my name is Mitchell Clark, and I'm one of the ECEN 325 TAs for the fall 2024 semester. Today we're going to be going over Lab 8 BGT amplifier configurations. So let's talk about what the goals are for this lab. So before in Lab 7 we learned how to bias BJTs with DC voltages so that we could place them in a specific region of operation. Most importantly, we were looking at if we put resistors or some sort of like current source, right, we could set these DC voltages so that we could try to place the BJT specifically in active region, which is an ideal choice for amplifiers. And whenever we DC bias, we want to set it up so that it stays consistently in this operating region so that we know the BJT is going to act a certain way according to the analytical equations that we have for how the collector currents work in active region, right? Now, what we're going to do in this lab is that because now we've learned how to bias them into active region, now we're going to actually look at them in AC to try to create amplifiers from these BJTs. And with this, we can set up the scene to learn about a lot of the basic amplifier configurations that we commonly use that helps us make up devices like operational amplifiers that we investigated early in the class. So how do we actually analyze these transistor amplifiers, right? Because there's a whole lot going on. We're supplying power, we're supplying our input signal, and we've got all these different effects going on, right? Well, like before, when we were doing a lot of complicated analysis where there's lots of different power supplies and such, we applied superposition, right? Because it allows us to take this complicated circuit that's got DC parts and AC parts, and let's just split it up into just let's looking at what the DC bias does on its own, right? And then let's look at what happens to the AC signal that goes in. And let's just look at these two things separately. We can apply superposition, right? And this is really useful for amplifiers because this is exactly the situation that's going on. We've got power that DC biases it, and then we got to separately evaluate what happens to the AC signal when we send them into the amplifier, which is usually the important part, right? Because we design the amplifier to have certain specifications, and that's important to the application that we're trying to make, right? But the big problem is that BJTs are not linear devices, right? They have an exponential like current relationship, right? So we can't use superposition because it only works with linear circuits, right? But what if we found some way to approximate the BJTs as linear devices? If we could do this, then we can actually apply superposition and make our analysis life a lot easier. Well, it turns out we actually do have a method of doing this. So this method that we have for linearizing how the BJTs operate is actually called the small signal model, right? We linearize the effects, right? So we only look at what happens in the linear region. We don't look at what happens in the higher order effects. And with this, then now that it's linearized, we can split it up into DC components. You can split it up into the AC components, right? Now, how does this analysis actually work? How do we just look at the linear part of what's going on, right? So let's first understand what we're doing, right? So I have my BJT here, right? And I set up a bunch of resistors such that I DC bias this device to have a specific resting base to emitter like DC voltage, right? So normally we set it up to have like 0.7, right? And I set up all the other voltages on this device such that it keeps it in active region, right? Okay, well when that's true, right? We then want to apply an AC signal to this, right? So now the new base to emitter voltage, it's made up of whatever the DC component was that I applied to it to bias it, right? And then now it's also going to have the AC component of whatever signal I'm injecting that I'm looking to amplify, right? And what ends up happening is that so let's look at this, right? When the BJT is an active region, the collector current is described by this equation, right? The sort of constant that describes how the current works for this specific BJT device, and then the exponent of the base to emitter voltage divided by the thermal voltage, right? And okay, let's go ahead and substitute in the fact that we're now applying a DC signal and an AC signal, which gives us IC is equal to IS e to VBE So we're accounting for the fact that we are applying the DC and the new AC part. And using exponent rules, I can actually split up this the VBE DC part, right, giving us IC is equal to IS E VBEDC VT, and e to the VBEAC VT, right? Now remember, the DC part is constant, right? We have our power, so it remains at a constant level, and the resistors are there that set all those voltages. There's nothing changing about it. It's how we biased the device. So we selected the sort of like operating conditions, right? So this is a constant, right? And this follows the exact same form of IC, right? So this is the quiescent current, or like the biased current, right? So we'll call this ICQ, right? Which leaves us with IC is equal to ICQ, so that constant part, EVBEAC divided by VT, right? So this is the equation that describes IC as we apply a changing AC voltage to the base, right? So this still is exponential, right? Nothing about this is linear. So let's actually apply a Taylor series approximation, right? So think back to, the end of Calc 2, right? So for our exponent relationship, if around, so let's apply a Taylor series for the exponential around the where VBE is 0, right? Because it's going to change a little bit around this region. So if we apply a Taylor series, and we get IC is equal to ICQ, 1 plus VBEAC, right? VT plus, what was it? The VBEAC divided by VT squared divided by 2, and then we get all these higher order terms, right? Now we want to linearize this, so I'm actually going to discard all of these higher order, squared and cubed terms from our Taylor series. I'm just going to look at the linear part. So when we do this, this gives us IC is equal to ICQ plus ICQ divided by VT, A, B, E, A, C. Sorry, not A, V. And when we do this, right, remember, we're just concerned about the AC part, right? So this is just some constant, right? The IC-AC part of the equation, right? Because now we can apply superposition, right? So this is the DC part, and this is the AC part. So I'm going to apply superposition because now we're dealing with a linear circuit. This leaves us with the AC part is ICQ divided by VT, VBEAC. Now what you might notice is if you remember the equations for this, this is actually called the GM. VBEAC. It's the applied voltage to the collector current gain, right? And this is one of the variables for our small signal model, right? So when we apply this Taylor series analysis to each of these terms, if you could apply it to the base, you could apply it to the emitter, we get components of this small signal model that we created, right? So if you apply it to the base, you get R pi. If you apply it to the emitter, then you actually also get like the T model, right? And basically this is the linearized circuit. So if we just look at the linear portions, what is this going to look like? Now, we've arrived at the small signal model, which describes how this sort of works, right? The textbook talks about this in quite a bit more detail. When we say small signal models, the reason is that because we've linearized it, we can't apply too large of a signal, right? The idea is that, remember it's an exponential relationship, right? So we're here along the curve, and in the DC we selected, somewhere along like the rising part where the current is pretty high. If we apply too large of an input signal, right? Remember, this is an exponential relationship, so the exponential part is going to start happening if we apply a large signal. But if we keep a small signal, we look at our linear tangent line, we can stay in between this space where the linear and the exponential are approximately the same, right? So the linear models the behavior so close that, it might as well be, what it is, right? So if we only apply small signals, then we stay within a region where the linear approximation is valid, right? So that way, now that we can consider it a linear device, then we can apply superposition to analyze these equations, right? And the textbook talks about this in immense detail, actually. So talks about how all the IV curves work, and then if you go down to the small signal operation, right, for the BJT case, you can see they actually go through this analysis. They do the collector current, which arrives at what I showed here, and this is exactly what I'm talking about. Is that in the linear region we stay pretty close along the exponential curve, where the linear tangent line approximates its behavior pretty well. So we apply a small sort of input signal to VBE to stay in this linear area, and then we can see how IC changes a lot in reaction to this small VBE change, right? So you can see how they also analyze the base, and that's where they get R pi. Then we can create the pi model, and you do the emitter, then that's how we get some of the emitter relationships. And then putting that all together, with a nice little clever construction, we can create our pi models, right? And then here they also account for the early voltage with the RO right here, being the early voltage divided by IC. That just comes from how the curve looks like, which if this is the collector 2 emitter and this is IC, that actually gives us the sort of slowly rising rate of change right here, which is basically just a sort of Ohm's law situation going on, right? So that's what gives us the RO. So all those things put together allows us to create the small signal model, right? And then after, the deal is that we've biased the BJT amplifier to be in active region, right? And then that small signal analysis then that follows after that uses those characteristics, right? So talking about, IC, like the quiescent current, right? Sets what all these variables are going to be after we apply our small signal model, so that we can look at what happens to the current as we bounce around that sort of linear region, right? So that's the development of how we've created the small signal models to simplify the analysis. So if you want to learn more about the small signal model and how we linearize it, I always recommend the Cedra Smith textbook. It's one of the textbooks that's listed in our class, right? But looking now is that now that we developed the small signal model, like what's the most effective way to use this? Well, so see this table here. There are three extremely common ways that we organize transistor is in amplifiers, right? So these are the ones that we're going to look at, right? And this includes the common source, right? Over here, the common base over here, and then the common collector, right? And what I mean by common is that this is the section of the transistor that is not outputting a signal or inputting a signal, right? It's the only one that's like sort of idle, right? And we use these configurations all the time, right? And so the small signal model is nice, right? But we don't want to use it every single time, right? We want to do like analysis, right? That's just like a lot of algebra work, right? So we don't want to do this every time. So just like how with voltage dividers, right, where we had like a signal, right, we had these two resistors like this, right? We saw this so often, we created an equation that we could just simply apply to it. Let's see if we can find what these equations are, right? These are exactly the same thing. Is that these are the input impedances, right, which are important, which you'll see later. And these are the transfer functions for these actually amplifier configurations that we can use over and over and over again in our analysis, right? And just like with the voltage dividers, right, this is something that you're going to use a lot. Now, we have the table right here, which gives you everything that you want, but I do recommend deriving these equations for yourself. It'd be fantastic practice for the exam, where you're going to have to, derive a lot of these relationships on the exam using the small signal model, right? But also if you derive it yourself, then you have a better understanding of it, and then you can know how to use it in the future, which if you move on to something like 326, you'll be using all the time. But on the exam, for example, like on exam 2 or the final exam, having these equations maybe just on your cheat sheet might be a great way to save yourself lots of time on the exam. And it's even better if you know how to derive it yourself, right? Now, doing the derivation, right, you kind of have the two different models, right? Some of the models make it easier. You have the pi model and the t model. Some of the models are easier to use for some derivations, and some are different for others, right? So if you're going to consider RO, right, so deriving these equations, usually it's kind of easiest just to use the t model, right? But if you are going to include RO, right, then you should use the pi model, right? And I'll go through one of these derivations right now, right? So what is it? So let's go ahead and do a derivation of just this basic like common emitter like current gain equation, right? So we have the BJT right here, and then we have the impedance of the collector, which goes to the output, and we have the impedance of the emitter, and then we have Vn right here, right? So we go ahead and apply our small signal model, right? So I'm going to apply the T model in this case. So you have alpha IE is equal to VO. You have Z collector, Vn, RE, which is also part of the small signal model, and we have the emitter impedance, right? And the deal is that, okay, from these equations, right, this is IE, we can recognize that IE is equal to the input voltage, right, across these two resistors because they're in series. So RE plus ZE, right? And VO is going to be whatever current is dropped across this collector impedance right here. So VO is equal to negative alpha IE ZC, right? And then we already determined that IE equals that. So then we get negative alpha VN ZC divided by RE plus ZE. And then this follows suit, giving us the equation that we see here in the table, right? So it's negative alpha ZC RE plus ZE, right? So I recommend applying a very similar method of analysis to derive these equations for yourself. And then remember, when it comes to finding the input impedances, right, what you're going to do is that, so if we had the case of the base here, right, you're going to apply a sort of a test source, so call it V test, and it has the current I test right here, right? You're going to find the base impedance, right, by using Ohm's law to do V test divided by I test. So just apply a test current into whatever input impedance that you're trying to find, right, and then go ahead and find this to give you your input impedance that you want. So highly recommend going through those derivations. So now I'm going to jump ahead just a little bit and look at something that's going to be a little bit more useful for Lab 9 or even in ECEN 326 if you take that class, is that, you know, now that we have all these linear models for the BJT amplifiers, you know, similarly to op amps where we simply just said, you know, you have this input and then it goes to this output, and that's modeled by the op amp gain just being AV, right? We can do the exact same thing with these BJT amplifiers now that we have these transfer functions that describe the gain. It makes things much easier, right? And it's very common that we will take these amplifier configurations, right, these BJTs, and we'll chain them together, usually for some sort of purpose, and usually one of those purposes is just simply to achieve higher gain. You know, we'll put multiple of these common emitter stages together to get a much higher gain, right? So let's look at like maybe a pretty common case, right? So where we have a common emitter, right? So this will be ZE1, and this will be ZC1, and then we have our input, and this chains into a common collector, let's say. This will be ZE2, that's where the output goes. And we have this. So this might be like a pretty common situation, right? And then since we have the values of what the gains are, right, we can simplify the analysis with the idea of two-port modeling, right? So the BJT amplifiers, we've got one input going in, and they lead to one output, right, where the relationship between these two is the gain, right? So we can model these things just like with the op amps, right? So you can write like a little amplifier signal or symbol, which just usually looks like a triangle, right? And then we can just assign the gain of the configuration there. So let's call this this gain AE, and we'll call this one AC for the port that they're common to. So AE, if we apply the input, and the output is just Vn times AE, and that chains into the next stage, like in series like this, AC, where now the final gain is just Vn AE AC is equal to the output, right? So we can just chain these together with these little amplifier symbols, and it makes the analysis so easy because we can see how they're in series and the transfer functions, or the gains, multiply, right? Now, one problem with this, though, is that we need to think back to Lab 2. We're doing a very similar thing where we had these first order transfer functions that we made with these passive filters like this. And remember, the problem is that, we were thinking, oh, well, we have two first order filters, so transfer function is just these two multiplied to give us a second order filter. But the problem was that because the first stage was not acting the same anymore, because by adding the second stage, some of the signal went forward to the second stage, which affected the properties of the first stage, right? And a very similar situation is happening here, right? Is that the two BJT amplifier stages are not perfectly decoupled, right? By attaching the second stage, the first stage is influenced, right? So let's sort of do that analysis, right? Like, this is where the input impedance comes in. So if I'm trying to find the gain of AE, right, I'm going to go ahead and apply the equation that's from our table. So negative alpha, right, and then the collector impedance, right? Well, looking into the collector impedance, right, now it's not just the ZC1. Now it's ZC1 in parallel with the impedance looking into this base, right? The impedance is dragged down by now the impedance looking into the base, which has a finite current, right? So now it's not just ZC, it's actually the parallel combination of the total impedance at this node, which according to our equation is going to be ZC1 in parallel with Z base of the collector stage, or the common collector stage right there. And then the rest of the equation kind of is still the same, right? So RE1 plus ZE1. And then AC, right? A very similar thing. Let's say we added some sort of, resistive load like this. We're going to drive something with this amplifier, so RL. Well, now the gain of that stage is going to be the parallel combination of what we see at the emitter. So it's going to be ZE2 in parallel with RL, RE2 plus ZE2 in parallel with RL. So, we're by using the input impedances, we're actually able to account for how the gain equations have changed by adding in these new stages, right? And with this method, we've significantly simplified analysis, right? Before, right, we had these, nonlinear circuits, and then we had these small signal models. It's like putting this together would have been an absolute nightmare of algebra to solve, right? But now we can just model this as two amplifier symbols with the input impedances looking into the two of them, right? And the analysis is as simple as, write the gain of each stage, right? See how the gain equations are affected by the input impedance looking into the next stage, and then you just multiply these equations all together, and then boom, you've analyzed what your circuit is. So we've avoided the algebra with the small signal model, and you've very quickly analyzed this multi-stage amplifier with these equations given here, just because we had derived what these gain values are. So now let's actually look at each of the common configurations in a little bit more detail, right? So the first one that we're going to look at is the common emitter configuration, right? This is probably the most common one just because it's great for amplification, right? It has a decently large input impedance, right? So it's good for multi-stage amplifiers. But one of the problems is, though, is that if RE or RG gets a little bit too small, then it heavily depends on what this input is, and with RE being a especially small value, the input impedance can kind of depend on this, but usually it's not too bad, right? The output impedance is pretty high, right, just being based off of whatever the collector impedance is, right? But remember, if we attach some sort of load to this, then the RO can go down a lot. And then very similarly, it's got actually a really, really high gain given by this equation right here. But one of the problems is, right, is that despite this high gain, the gain is largely based on whatever the collector impedance is, right? And if we attach some load to this, then it becomes RC in parallel with RL. And if RL is extremely small, which there are some applications where that's true, then the gain goes way down, right? So is there any way that we can, sort of deal with this? I mean, heck, even worse, right? If we have any sort of RE or RG, that also brings the gain way down. So, how do I, navigate not ruining the gain of this stage with some sort of load impedance being attached, right? And usually that feeds into the common collector amplifier, right? Now this right here, this is like a design procedure for the common emitter, which we'll talk about a little bit later, but let's look at the common collector configuration. This is also known as like the source follower, and the reason for that is because it's great for buffering, right? It's also got a similarly really high input impedance, right? But it's very common for this stage that RE is going to be very, very large, because what you notice about the gain equation is that it's actually just a voltage divider, right? It works just like a voltage divider, so because of this, the gain is low, right, and the impedance is high because we're going to make RE big, so all of the signal goes to the output, right? Because this gain is always going to be less than 1, but if RE is really, really big, then it's going to be about 1, right? So usually RE is going to be big, which means that the input impedance is big, which means that it's going to be great for buffering because now, if the input impedance is big, then the gain of the previous stage, for example, like a common collector like this, is also going to remain really high. It's not going to be dragged down by the, for example, maybe really low load impedance, right? So that's kind of like the trade-off here, right? Is that we add this extra source follower stage to act as a buffer, right, of the load impedance, right? So the gain of this stage is going to be pretty bad, right? Especially once we attach the RL to it, right? But that's kind of the L that we take so that the gain of the the common collector stage can remain really high. And overall, this is like a net benefit, right? And what's also nice is that the output impedance is especially low, which for some applications where the loads are really, really small, think about like radio frequency applications, right? If you've taken 322, you might know how important it is to match impedances properly. Well, this is going to be a case where it's nice because the impedance can be pretty low. We can get it to around 50 ohms or whatever we're trying to match, and leads to a pretty good deal. So source follower is very good for buffering your output, and amongst some other more complicated amplifier configurations. And then lastly, we also have the common base configuration, right? And similar to the common emitter, it's got really high gain and it's got really high output impedance based off whatever the RSC is, but the input impedance is laughably low. So it would affect the gain of the previous stage. So why do we even talk about this? Well, because it actually shows up in a really common but more advanced transistor configuration called the Cascode configuration. So we have a common emitter amplifier right here, right? And then it leads into a common base amplifier right here. So we get VO, and then we have some sort of like RC right here, right? And the idea is, right, is that Cascode is really great because the output impedance is like ridiculously high, right? If we look at the output impedance, right, we have, if you look at our table, right, the impedance looking into a collector is infinity, right? Well, it's not actually infinity if we consider RO, but it's really, really high. And the deal is that we've got two infinities nested into each other. So the output impedance is like infinity squared, right? So the output impedance is ridiculously high. And because of that, that also makes the gain extremely high. So that's where this situation sort of shows up, is that normally we have the common emitter followed into the common base leading to this Cascode configuration, which gives us really high gain for just these two transistors. And it's got a couple other nice effects that you would cover in higher level courses, right? So that's where this configuration shows up a lot. So now let's go ahead and talk about the calculations that we're doing in this lab, right? So we're designing a common emitter amplifier in figure 4a, right? This is the main part of the pre-lab, right? So you make your design, right? It's got to meet these specifications, and then you'll just copy paste those values and specs that or the values for the components that you found just into these other configurations, right? So this is the main portion up here. This down here is going to be relatively straightforward, like plug and chug, right? And what's nice is the lab manual actually provides a design procedure to do number one here. It's not my favorite design procedure, right? So I'm going to provide my own after this one, but we're still going to go ahead and talk about it because it might be a little bit more straightforward for people who are struggling a little bit, even if it kind of hand waves a lot of the nuance, right? So we're trying to design this circuit, right? And what's happening is that we are going to apply some small input sine wave Vi, right? And then the output is going to exist at whatever this DC collector voltages, right? And then we're going to amplify it to swing around this point like this, right? And the main deal is that we need to select the output DC voltage, right? Such that when we're swinging around this point, we don't hit the power supply at the top, and we don't push the collector voltage too low, such that the collector to emitter voltage is too low to push the transistor in saturation, because that's how we get distortion, right? Now, I think one other common thing in confusion as well is like, what are these like infinite capacitors, right? Remember, capacitors block DC, right? Because they'll charge and then they fill with the DC and then they displace it, right? So the whole deal is that we say this infinite capacitor, right? You know, when we consider just the DC, right, the capacitors are open, leaving us the DC component right here. When we're looking at AC, the capacitors end up being shorts, right, because their impedance is 0, right? So that just gives us the AC component right here. So it's purely just a modeling choice to show how we decouple the two effects in our analysis, right? So you'll just pick like a large capacitor in your simulations, like a 1 farad capacitor or something like that, and just leave it like that. So let's talk about their design procedure, right? So they go over the typical specifications, and these are all the same ones that are required of us in the calculation section, right? So we're going to try to have an unclipped voltage swing, right? So remember, the voltage swing can get too high such that it hits the power supply, and it can get too low such that it reduces the collector to emitter voltage, right? And because of that, that ends up causing THD, right? Because it won't look like a pretty sine wave anymore. So we have to worry about that. We have to design for that. We also want to design for a specific voltage gain and then specific input and output impedances so it works correctly with our application. And then we also want to make sure it's not sensitive to any variations so that it works in lab, but also from the idea of like an industry, you know, we want it to work the same way every time, no matter which customer we give it to, right? All right. So let's go through their design procedure. So first we got to pick VRE to be kind of large, such that if the base to emitter voltage does change quite a bit, then there's a lot of room for fluctuation, right? So this is just a nice big buffer so that in case things vary a lot, then we've got room to spare for these effects, right? So you can kind of take this at face value, right? Then, right, what you might notice about this design procedure is that we're just going to go one after the other of picking specs, right? One thing into the next. So first we picked VRE, right, which is going to be this voltage at the emitter, right? Then we're going to pick our output swing. So you have the VRE here, and then you pick the output swing that you want, such that now that you can pick the VRC. So the output swing has to exceed 1 volt in either direction, right? So you're going to be given an equality for VRC, which you will then go ahead be influenced to pick, right? Because they go ahead and say, let's just keep RG as 0 because that maximizes the gain equation, right? Leading to this expression right here. So just pick the maximum value for VRC that you can, right? To go ahead and maximize your gain, right? And then the collector to emitter, right? You know, to make sure we don't go into saturation, right, let's like increase our buffer, right? It's up to like 0.5. So change 0.2 to 0.5 because this is the saturation voltage, right? So you want to improve that buffer to make sure that when we're swinging between the two, we don't push the BJT into saturation region instead of active region. Afterwards, then we're going to try to pick what our IC is, right? So you have to pick what the beta is. You know, worst case scenario, it's going to be 100 as given in the specifications, but you can pick a value between 100 or 200. The design is going to be beta insensitive anyways, so it's not too big of a deal, right? And lastly, we also want to make sure that we pick an N value. And this N value is just like what we did in last lab, where we selected the base resistors to have a current through them that's much larger than what the base current is. That's the whole deal. The N is just the multiplier between these two things, as you can see here. So we want to pick it large enough such that if beta changes, right, then the base current will change accordingly and not pull too much current through the resistors such that they don't act like a voltage divider anymore, right? And one nice thing is that, like, if this is cool, if you pick the same voltage for the collector and emitter voltages, then IC doesn't change the output swing, but can change the resistances. So that might be a nice thing to consider in your design, that if you keep them the same, then things might be a little bit more straightforward. And then at this point, you've selected practically every value under the sun. So then there you go. You can calculate all of your different values right here to get the components that you need. And then lastly, what you might find once you build it in simulation is that RG is going to be important because the gain is likely going to be way too high. So you increase RG to bring that gain down to 25, like they ask for. Okay. So that's their design procedure, and you can kind of just follow this, and you will eventually reach something that works pretty well, right? And then you'll tweak it in simulation to ensure that it meets the specifications, because that's kind of how this whole procedure works. Is that we will design a circuit, we'll do it like 10 minutes or so, make a lot of assumptions, and then we'll go to the simulator and tweak things till it meets the specification there, right? So design according to the specification in your calculations, and then in simulations you will make edits to ensure that it meets the specifications there. So now I'm going to go ahead and go over my personal sort of design procedure, right? So usually what I would like to do is that I would like to address each of these specifications one by one and see what each of them sort of mean for our relationships, right? So let's start with the 0 to peak output swing, right? So VO has to be greater than 1 volt, and we're also worried about the THD, right? So the main deal is that the location that we position our output voltage, right? We need to make sure that we position it such that the output swing does not hit the power rails and doesn't put the transistor in saturation, right? So the deal is that the difference across this resistor to VC, so the difference across RC, 5 minus whatever the voltage is at C, has to be greater than the voltage swing that I want, right? Such that it doesn't swing more to clip at the power supply, but it has to be less than enough of whatever the voltage is down at the emitter, right? So that's going to be the power supply 5 volts minus the swing minus whatever the emitter voltage is, right? So VRE, and then minus whatever the saturation voltage is, right? So that leaves us with the range of values that we can pick for whatever VC is, right? So then we also want a gain of AV, right? So AV is equal 25, right? Okay, well, from what we know about our equations, right, we know that AV is going to approximately equal RE. I know there's a negative sign there, but we're not really worried about the inversions. I'm just going to leave it out. RE plus RE in parallel with RG, right? Now, RG, this kind of just comes from experience a little bit. RG is always historically going to be an extremely small value. There's no reason it's probably never going to be more than 50 ohms, right? And it's very likely that RE is going to be closer to like 1K, right? So because of this, really this is probably going to be more like RE over RE. Oops, sorry. RC. RC is going to go in the numerator. So really the denominator is going to look more like RE plus RE, RG, like this. Because if you have two parallel components and one of them is much smaller than the other, then it's just going to be the smaller one, basically. And then because of this, we can just apply our equation for what RE is to end up giving us the relationship negative RE IC. Forgot, I'm going to ignore the negative sign right there. Right? And then put VT plus RG IC, and that has to equal 25, right? Okay, so then what's next? Right, so this is the equation that kind of describes what the gain is going to be. So now the input impedance, right? So greater than 2 kiloohms. Well, knowing the equation that they give us in the lab manual about what the input impedance is, Rn is going to equal RB1 parallel with RB2 times beta plus 1 VT divided by IC plus RG. And the reason why I don't like their design procedure as much, even though it's a little bit more straightforward, is that they start with the assumption that RG is going to be 0 just to change it later. But when you do that, you kind of make your input impedance specification a lot more difficult, because then you're just left with this term times beta. So it's going to be extremely low, making it kind of hard to meet, right? So like I said before, their design procedure is much more straightforward for when you're learning, but if you want a little bit more robust design, you can kind of take a look at what I'm providing here, which is just supposed to kind of provide a little bit more context about what we're thinking about when we're designing, right? And that has to be greater than 2 kiloohms, right? One of the things that also just kind of comes with experiences is that like low beta is only ever going to hurt us. So I'm just going to assume that beta is the lowest possible for the spec, so 100, right? So this leaves us with the relationship for Rn being 5. Well, sorry. Now we're going to take a look at the current, right? The beta current. So the current that goes through these resistors, right, just like last lab, need to be at least 10 times bigger than the actual base current itself. So I'm going to write out that relationship is 5 divided by RB1 plus RB2 has to be greater than 10 times whatever the base current is. Right? And because we assumed that the beta is the lowest, it's going to be no more than 100, right? This transforms this relationship into 50 divided by RC has to be greater than RB1 plus RB2, right? And then lastly, one of the last things that we can identify from our spec is that we have the output impedance, right? And the reason why it's the last thing is because by picking just like what they said in the lab manual, by picking a VRE greater than 1, this should be okay. And THD is not really something that you can calculate for. It's only something that we can preemptively design for. And we're worried about that primarily with what we pick here. So we don't need to really consider it too much more beyond what we're going to be doing in simulation, right? And then lastly, we're trying to calculate our output impedance, right? So RO is going to be less than 1.8 kiloohms, right? Well, what we know about our equations is that RO in this case is just whatever the value of RC is, right? So simply RC has to be less than 1.8 kiloohms, right? Nothing really important for us to be doing there, right? And then as I said earlier, so that we can be ready for any base to emitter voltage variations, right? We're going to say the VE has to be greater than 1 volt, right? And because of that, that also means that IC RE has to be greater than 1 volt, right? So I've laid all the equations out in front of us, right? These are all the relationships that we've identified. And now that we've taken a look at everything, now it's safe to start picking values, right? So unfortunately, it's not as nice as last lab, where we could directly solve for what the relationships of what the inequalities for the resistors are, right? But we've identified all the relationships that we can. And when we do that, now we're allowed to start picking values and seeing how that affects our other relationships, right? And if we pick a value that, limits something else too much, then we know how to start from the beginning to go ahead and fix from there. Or more importantly, when we get to simulation and something's wrong, then we have our relationships to reference here to see what do we need to edit to sort of try to fix that. Because for this lab, the biggest problem is likely going to be meeting the THD spec, right? So it's going to be really important that you kind of pick a collector voltage and an emitter voltage until it starts working. So you're going to have to play with that quite a little bit. You might have to recalculate a couple more times. And if you have these equations already with you, then you've already done all the legwork, right? You kind of have a much more intelligent understanding about what you need to change in order to get that to work. So my advice is if you do follow my design procedure, you can start by picking your emitter voltage, right? And once you pick that, then pick a output swing that you want. When you do that, that gives you a collector voltage that you can end up picking, right? And then once you do that, if you choose a collector current, then you can go ahead and pick your collector and emitter resistance, right? And then once you're left with that, you can directly calculate what RG is going to be from the gain equation, right? And then lastly, once you've done that as well, you can calculate what RB1 plus RB2 has to be from the equation for the Rn. And then once you've sort of decided what that ratio is going to end up needing to be, right? Because we weren't able to minimize this equation down too much, but now that we've decided what the collector and the gain resistor are going to be, then we can make a much more intelligent understanding about what it needs to be at a minimum, what the Rn needs to be at a minimum, right? Because if we pick RB1, RB2 to be too small, then Rn is going to be way too small. So RB1 plus RB2 needs to be less than a certain value to supply a certain current, but needs to be greater than a certain value to give us the input impedance. And then we can pick what RB1 plus RB2 is, and then SEPSENA is going to be able to pick RB1 individually and RB2 individually according to the fact that the base voltage has to be the emitter voltage plus 0.7, right? So you can go ahead and calculate it. You can go ahead and calculate it with RB2 divided by RB1 plus RB2 divided by 5, right? So then you can get your VB right there, which needs to be 0.7 greater than whatever your emitter voltage is, right? So you can sort of follow my design procedure, and then you can reach what I've got. And then once again, you might need to play with your collector emitter voltages that you picked at the beginning, right? To give you a THD that meets the specification in simulation, right? So there's just going to be a lot of finickiness of that, but that's just kind of how design goes. So if you've looked at the two different design procedures, the one given in the lab and the one that I've talked about here, and you're kind of trying to pick, which one should I go with, right? I think the design procedure that they give in the lab manual is a little bit more straightforward to follow. You kind of just be able to pick one after the other and then address each of the equations. You'll be able to pick one design variable after the other and then address each of the equations, right? And then each of the things just kind of flow into each other. And I think this design procedure does a really good job of kind of trying its best to assign inequalities to everything as you pick your values, right? Especially here for the collector current. This is a relationship that's a little bit more difficult to derive, but kind of does a lot. Meanwhile, my design procedure, I think, kind of takes an overview look at all the equations, right? And then you can kind of start to pick values to see how each of these relationships change as you pick stuff, right? It doesn't do as good of a job of like identifying different inequalities, right? Like, collector current just kind of gets picked a little bit on a whim, or just kind of from on your experience, right? You're just seeing how it affects the variables, right? But I think it's also an alternative perspective if you're not fully vibing with what they provide in the lab manual, where they don't give as much explanation, right? So I'm not saying mine is better or the lab manuals is worse, but it might be an alternative way of thinking about solving the problem, right? Both of them are going to lead to valid results that you're going to ultimately have to play with anyways once you reach simulation. So now finally, let's take a look at the simulations that we need to do for this lab, right? So you already went through the legwork of designing what's in figure 4a. The simulations are basically just applying the exact same component values you already designed to each of these circuits, right? So it's a bunch of stuff to simulate, but if you look carefully, right, each of these sections are the exact same simulations that we're asking you to do. It's just take the components that you already designed for this one and then apply it to each of the other designs, right? So pretty straightforward, just quite a bit of work to do, but something that you guys haven't done before, right? So DC operating point you can use to get the sort of like the table, just like in the last lab. I also in last lab mentioned not using really interactive simulation, but I actually saw a lot of nice stuff as well. So that one you can enable interactive simulation, then add little voltage probes, and it will show it all on the schematic as well. So that's a nice little view that you can use. So pick your choice, doesn't really matter too much. Perform AC simulation to get the gain, the RI, and the RO, right? Getting the input and output impedance in simulation is actually a new thing. So if you reference the MS82KSO document that we have on the canvas, right, they describe exactly how to do these simulations, right? So with the input impedance, right, so you keep your circuit set up as normal, right? But then what you end up doing is instead of trying to calculate the gain by applying VO, you need to add this expression into the expression manager, right, for the simulation. And the reason why this is the expression for RI, right, is because for this voltage source, we always pick the AC magnitude to have a magnitude of 1. So this equation right here is effectively just Vn times In, so that gives us Ri. And then you'll end up getting a Bode plot, right? I recommend changing the vertical scale to linear, right, instead of dB for this. So you'll get a little Bode plot, right, that might look something like this, and then pick your input resistance as the flat value at the bottom, right? And the very similar thing for the output impedance. So in this case, we apply an AC current source to the input. So remove your input signal, right? You apply an AC current source, and the magnitude of VO is the output resistance, RO, right there, right? Because if we end up applying VO, VO is simply equal to RO times IO, right? And we plugged IO in as the input. So effectively what we're evaluating is VO divided by IO. So that means that VO in our simulation is going to give us RO. So you're also going to get a very similar Bode plot, change it to linear, and then pick the lowest value at the DC right there. So that's how you do those two simulations. It describes it step by step in this manual right here. And everything else is exactly the same. So it also talks about how to do Fourier simulation, which y'all did have done before. This lab manual talks about it specifically, right over here. And remember, like in the simulations, as I mentioned before, this is probably going to be the most troublesome, right, is meeting the THD spec. So once again, play with your emitter to collector voltages, right? Your collector might have to be a bit lower to, lower on the voltage range to try to get what you need. So just tweak things a little bit until they work. Maybe go through the design procedure and redo some calculations, and then eventually you will meet the spec. Because it's really important for lab that we have the circuit already meeting specification in the simulations, right? Because otherwise it's going to be very hard to change things on the fly in the lab, right? So just try your best to meet everything in simulation, and then come to lab with a circuit ready to go. And then you should be able to find success as we start getting into the harder labs. So good luck.